welcome. Thanks for coming here. It is my great pleasure to introduce you to Pavel Panchaha, who is a PhD candidate at the University of Washington, right across the lake here. Pavel has done a lot of great work all across the spectrum of the programming languages research, from program synthesis for web technologies to constraint solving to numerical tools, which he'll be talking about today. And I suppose, Pavel, just take over now.
Great. Yeah, so as Alex mentioned, I'll be talking about approximately half of my research today. The other half on synthesis for CSS, and also verification and so on for web technologies is a totally different line of work. I'd love to talk about that too. But today I'll be talking about my work on floating point and numerical analysis. And this is a sequence of papers and projects I've done with a bunch of co-authors, without whom it wouldn't have happened. So big thanks to them. And mostly, this line of work can be summarized as building numerical tools, but for non-numerical experts. And really, this work builds on this great success, which is the invention of floating point arithmetic. Some of you have seen this slide before. The point stands, though, that floating point is used pretty much everywhere, from medicine to finance, transportation. Floating point is what we use for mathematical computation, pretty much exclusively. And so that means it is also what will take us to Mars, what will control our robots, what will allow our cars to drive themselves. And the reason that floating point has had such a big impact, the reason it's so widely used and so beneficial, is because it has enabled this great democratization of mathematical computation. Right, floating point arithmetic means that computations that used to require numerical analysis expertise in order to do correctly are now something that most people can do without numerical analysis training. And that's because floating point arithmetic is accurate enough, often enough. So of course, there's a great benefit in having people without specific expertise being able to do mathematical computation. But there's also a downside, and that's that often enough part, which is that when you fall into one of these cases where floating point arithmetic isn't sufficiently accurate, you don't necessarily know what to do. So here's an example of that. A friend of mine, Harley Montgomery, he's a machine learning researcher. A few years back, he was working on a new clustering algorithm. And in this plot, you see both the starting cluster and the ending cluster after clustering. And the problem with this plot is that it doesn't show that any clustering at all has occurred. Everything stayed in its initial cluster without change. And this was odd because Harley could actually mathematically analyze the clustering algorithm he developed. It was supposed to work fairly well. So he and I chatted, and we discovered that the problem was floating point rounding error in one key part of the algorithm called the transition matrix. And that was being computed in a way that didn't correspond to what that computation would look like in the real numbers. So when we fixed that one numerically inaccurate expression, the clustering algorithm immediately started working correctly. And you can see that here because there are some large blocks that are fairly dark. That means you consistently get those results.
So in this case, the rounding error was during the optimization. It was
that's right.
It was optimizing the wrong loss function, or so.
It was an MCMC algorithm. So there's a transition function involved in that, and the transition probabilities were not being accurately computed. So it would too easily get stuck in a local minimum and find itself unable to work its way out.
I see.
So machine learning is obviously one place where we do a lot of numerical computation, where even though we are normally resilient to errors, floating point error can happen and cause otherwise sound techniques to fail. Here's something from the other end of the spectrum. Blake Corder is a CAD engineer, and he has a hobby of making these mathematically inspired artworks. So here, the design on this pair of rings is found by evaluating some complex function. Of course, the design is computer generated, so he has a program that produces that design and the CAD instructions for milling it. And when he first ran this program, it produced output that looked something like that. So again, you've got this weird noise and banding. You do not want to put that on your finger. And that, again, is caused by floating point rounding error. So I got this example over email. He emailed me to say that he'd used one of our tools. It helped him find the error and then fix the error. And that gave him this plot, which is more or less what gave him the final design to put on the rings. So to zoom a little out from these two examples, this democratization of computer arithmetic has had a lot of obvious benefits, stemming from the fact that floating point numbers are pretty easy to use. It's pretty easy to write programs that use them. But there have been some downsides, which show up in cases like this. That's cases where floating point arithmetic leads to programs whose behavior is hard to understand because floating point arithmetic doesn't exactly correspond to real numbers. It produces problems that are hard to debug, especially, again, for users like Harley and Blake who aren't numerical analysis experts. So that is what pushed me toward this goal of building numerical tools for non-numerical experts. Again, of course, people with expertise in their domain, but not numerical analysis training, which is the majority of people using floating point today. And I'm not the only person to have this broad idea. The research area of floating point analysis has become quite big over especially the last few years. And this is partly due to some technological advancements and partly due to renewed interest because of deep learning, robotic control, and all these new applications. And in this talk, I'm going to focus on two projects that I've done in this space. Herbgrind, whose goal is to find root causes of floating point problems, and Herbie, whose goal is to help you fix those problems once you've found them. But I'll get back at the end of the talk to this broader vision. So let's start with Herbgrind. And before I tell you even what Herbgrind is, I want to walk through what it's like to debug a numerical problem. And as I do this, picture yourself as someone who doesn't have a lot of numerical expertise, but of course has this wealth of domain knowledge. And I'm going to pick a very simplified example. This is a program that I wrote a few years ago that plots complex functions.
So just as a context setting question, okay, so when I was in computer science, undergrad, they actually taught numerical computing as a course. It was a required course. And at that time, the world was sort of split into the numerical computing part of computing and the other, which was like accounting and all the things, systems. But and I was at RPI, so there was sort of this engineering emphasis, so that was part of the story. So the first question is, how often is that course taught these days at universities?
So I took a computer science major in college as well, and that was not a required course. Okay. And it was taught, but it was taught by a physicist, which I think tells you a little bit about who the audience is. When you think about, there's so much more that we program these days, right? Anything from transportation systems to web apps and so on. And there's this much broader spectrum of what computer scientists need to know. So I think that's necessarily led to there being a lot more programmers without specific numerical analysis expertise.
Okay, so that's sort of the follow-up then is, okay, so this is not taught. So when you talk about non-experts, you're talking about every programmer, basically.
Oh, yeah. Yeah.
So that's important to distinguish. Because, and the other side of it is, but this may be, to the relevance of the topic, is when I was being taught, one of the stories was, well, when you need to write this numerical algorithm, like, I don't know, like a Newton's method or something, you have to think about this when you write the loop, right, about, the error bounds and things like that. And most of that sort of hard thinking has gone into libraries.
Yep.
Right, so I just call the library, I don't have to worry. So there's two levels. There's here's the representation of numbers, and here's the library that does, Newton's method or whatever, any kind of arbitrary array computation that, where the person who wrote the algorithm, had that insight. So how much, am I, as a normal programmer, am I just totally kind of protected from that? Yeah.
I think that's a great question, and it gets to the heart of why numerics is interesting and interestingly different from some of the other challenges we tackle as programmers. When you're thinking about take cryptography, which is something you don't want ordinary programmers writing. That is something we can hide in a library and give very clean abstraction boundaries. Numerics is interesting in that often problems occur at the interfaces between otherwise accurate components. If you think about it, the fundamental operations your computer executes, addition, subtraction, maybe you can think of some library functions like exponentiation. These are all accurate, or as accurate as they can possibly be. Yet combining these together still produces problems.
Okay.
And this happens at a broader scale as well. Solvers, matrix libraries, each of them internally might be as accurate as you could reasonably ask. But the particular inputs you give those tools can sometimes cause numerical problems. So maybe we'll actually see a little bit of an example of this. So I have this example program. And its goal is to take functions from complex numbers to complex numbers and plot them. So it should produce pictures. And in some sense, this is a very simple program. But nonetheless, it's easy to, even writing a relatively simple program at just evaluating a function on a lot of input points, run up to numerical problems. And in fact, the way I wrote this program originally accidentally introduced a bug that made its output look something more like this. And this is not only wrong, it's even nonsensical, because that function's continuous, and this sort of stippling effect shouldn't possibly come up. So how do you figure out what's going wrong in a problem like this? Well, we can start at this program output, which we can clearly see is erroneous. Something's going wrong. And we first need to figure out where in the program that problem is happening. So this plotter program, despite being fairly small, already has a bunch of components in it, from generating input values, interpolating the computed outputs, and generating this bitmap. And between these components, we've got several libraries for complex arithmetic, for generating bitmaps. We've got some data types, and we've got some complex memory layouts. So let's say we can identify the component. In this case, it's the component that computes that complex function. So inside that component, we're doing a lot of mathematical computation. And most of that computation is correct. So we start with this expression. And it turns out that to evaluate this expression, we're actually going to solve this quartic equation. And it turns out that to solve this quartic equation, we're going to use the quadratic formula. And it turns out that in this particular case, given the particular inputs that we sent to the quadratic formula and the input range that we're plotting over, we're using the quadratic formula for cases where b is greater than 0. And as it happens to be the case, this form of the quadratic formula, which is the standard one but not the only one, for these particular inputs, can exhibit a problem if a certain relationship is true about the other components. How's that for a library? So in order to debug this problem, we actually had to figure out the source of the error. We had to figure out the expression that's being computed that's causing this error to occur. And we had to figure out the input ranges that expression is being computed over. And the goal of Herbgrind is to give you the same information without requiring this debugging process, which, of course, in a lot of cases, you'd need some numerical analysis experience just to do. So here's what Herbgrind would give you on the same input program. First, it would give you the program output that it thinks is erroneous. So here it's pointing to some comparison instruction, and this happens to be inside the bitmap generator, that it thinks about half the time is producing the incorrect value. And that turns out to be why you get this weird stippling pattern. But we already know the program output is erroneous. This is not the useful bit that Herbgrind gives you. What Herbgrind gives you is a root cause for that problem.
Wait, just to understand, how did it know that the program was erroneous in the first place?
That's a great question. I'll answer that in just a moment.
Okay.
Yeah.
And then, well, I mean, obviously the follow-up is, why did it decide that that compare function was erroneous? Right? I mean,
yeah.
Okay.
So these are fantastic questions that I'll answer in a moment.
Okay.
So what I want to do is actually step through each part of this output and tell you how we got that part of the output. How did we figure out that the output was erroneous? How did we figure out what part of the code caused that, the root cause? How do we figure out what it was computing then and what the inputs were? And the basic framework in which Herbgrind is going to do all of these steps is in the framework of a dynamic binary program analysis. So Herbgrind's view of the plotter program is something like this. I don't like reading x86 assembler. I'm not going to force you to either. So let's actually look at this assembly as something a little more abstracted like that. So the fact that Herbgrind is a dynamic analysis means that it will execute every instruction in the program as the program itself would execute them. So in fact, it's going to take one of those instructions, for example, this subtraction between registers 4 and 2 into register 4. And for these registers, it's going to look up the floating point value that those registers would store, then do the operation in floating point and get the floating point output. But we're also going to annotate every floating point value in memory in registers with some shadow memory. And that shadow memory is going to store higher precision values. So I'm calling them real here. They're actually just higher precision. And every time we do an instruction, we'll also execute a higher precision version of that instruction on the higher precision inputs. So here, higher precision is implemented using the MPFR library for arbitrary precision arithmetic. Because we have a floating point and a higher precision or real value for every floating point value in memory, we can look at the difference between the two and know, is this value erroneous and by how much? So for the compare instruction that you see here, what Herbgrind can do is say the real valued correct value of this floating point amount would produce a different value in the comparison. So it would be less than instead of greater than, for example. And it's in effect this escape from the floating point world into the world of strings, integers, booleans, any other discrete value that lets us detect that some erroneous output is happening.
So the underlying assumption that if it changes the control flow, then it's basically not intended.
Yeah, we have sort of an implicit spec that you're not a floating point expert. You meant this is effectively real numbers, and your divergence from that is surprising.
But I mean, but it's kind of arbitrary, right? I mean, if it's off by 1% and your comparison doesn't catch that, then it's not. Then you wouldn't call it an error, right? Is there a more principled way to basically say, it's far enough off that we care? I mean,
effectively, okay, so of course, Herbgrind itself has some thresholds you can set to reduce or increase the amount of output it produces. But we can also make a more principled claim that your program runs for a while, and then it has some forms of effect, and it produces output. So output is a screen. In principle, it could call different system calls, et cetera. Any difference to those effects or outputs is what you care about. That's what we call an error. Because in effect, you otherwise treat the program as a black box. And we have in the paper a little formalism where we show that any sort of escape out of pure floating point computation into some form of output or system call is what we're going to catch.
And the definition here says that any input, it doesn't have to, it's like, it may be the case for most of the inputs I care about, it's fine, but there still exists some input.
Sure, and that's part of why we give you this additional information, right? Both this information that half the values are incorrect, and there's a lot of them, seems to suggest that this is happening a lot and wrong a bunch. And also for these intermediate values, you can see what inputs are problematic and also what inputs are the broad range.
Okay, so you're not doing a range analysis, right? You're just looking at specific concrete values that flow through the operation.
Yeah, it's a dynamic analysis, so we're operating on a particular input.
You're not saying that, so where does the range come from?
We'll get to that. It's number 4. Yeah, I'm glad you're excited. Yeah, you asked a lot of questions, so let's pop the next one off the queue, which is now that we know that a program output is inaccurate, right? Like this picture is incorrect. How do we figure out where in the code that came from? In other words, we want to tie the end of the program, something incorrect was outputted, to the middle of the program where the wrong computation was done. So let's go back to our picture of executing a single instruction. And to determine whether this instruction introduces error into the output, we're going to start with these higher precision inputs, because the higher precision inputs don't have error added to them. We don't want to blame this instruction for errors that have already occurred. So let's start with these higher precision inputs. And from these higher precision inputs, there's two ways we can imagine computing an output for this instruction. One way is that we can round the inputs to low precision and then execute the operation on those inputs. The other thing we could do is we could execute the instruction in higher precision and then compare those two output values. So the gap between these, between whether you do the operation in high precision or low precision, or if you really want to get into it, whether you incur this rounding or not, that's the difference between those is what we call the local error of that instruction. And the key is that it corrects for this garbage in, garbage out property. You'd expect erroneous outputs if the inputs were erroneous. But here we've effectively reset the error on the inputs to the correct value. And that's allowed us to detect whether error comes out, thanks to this instruction, whether or not error was put in. So this can tell us whether a particular execution of a particular instruction was problematic. We want to tie that to the program output. And the way we'll do that is effectively adding another piece of shadow memory. Not only are we going to carry around real numbers, but also these influences from prior instruction executions. So every instruction that we execute that has a lot of local error, we will add an influence to the set of error sources of its output. And we'll also pass along anything that influences inputs because, again, of this garbage in, garbage out property. So in fact, this is a dynamic taint analysis. Right? That's really what we're executing. We add new taints every time high local error occurs. And otherwise, we aggregate them through program flow. And there's a few tricks we throw in here to deal with some additional numerical idioms. So you can imagine, for example, people sometimes use double-double tricks that introduce error in one part of the program to cancel out error in another part. And that sort of thing can be handled within this dynamic taint analysis framework, effectively by removing some taints when we verify that they're not real error. So that points out a location in the code. And what location in the code here means is a particular assembly instruction. You can't really tell a user, go fix this assembly instruction. Not that many people are fluent readers of assembly. And then what does that even mean without some numerical analysis expertise? So we want to pull out additional information to give the user context. What operations are being executed on what inputs? That's something they could take to either a numerical analysis textbook, a friend who can help them, or perhaps some of the tools they'll be showing off later. And the first bit of context is what operations are being executed. I mentioned in an answer to your question about libraries, Ben, that often floating point error happens across function calls or across components. So when we extract this expression, we do want to cross function boundaries, data structure boundaries, memory reads and writes. So we're going to generate this expression being evaluated dynamically as well. So that means that we're going to have one more piece of shadow memory. To each floating point value, we're going to associate a trace of how that expression is generated. And we'll build that trace every time a floating point instruction is executed. So here, this expression is generated by subtracting these two expressions. So this trace is going to be gargantuan. It's going to be the full history of your floating point value. And giving it to the user would be maybe worse than nothing, because it would scare them. So we want to abstract this out to something more understandable. There's a second issue, which is that this handles a particular execution of this instruction, but we're going to execute this instruction several times. And we can kill two birds with one stone by making use of the multiple executions to abstract the expressions. So what we're going to do is we're going to try to go from these to these, from these concrete expression traces to this expression that's abstracted and has variables. And we'll introduce those variables precisely when different executions of this instruction differ. So for example, you can see that, I don't know if you remember the full quadratic formula, but normally there's a variable here, a. And that's disappeared because in every instance that it's used in this program, that variable is set to 1. You can also see that here we detect some repeated variables. And that's crucial. It's very important in numerical analysis to detect these, because often problems come up from reusing the same value in 2 places in a way that eventually causes them to cancel. And that, again, is something we're going to pull out of these expression traces by noticing that the traces are identical. So that gives us these expressions. And the final question, Ben, we're getting back to yours, is how we get these ranges. And you can see that now that we have this expression, and now that this expression is available at a particular instruction, getting these ranges is going to be a lot easier. In effect, we can take this expression, this abstract expression that we've associated with this instruction, and use it to figure out where in this expression trace was B computed, where was C computed. Those locations in the trace are going to be associated with the floating point value of that expression. And so we can use that just to update our running range.
So it's just a dynamic measure of the
Exactly.
range, which it gave an answer that was.
That's right.
It's only the times it was incorrect.
So actually, we give you both, and I'm sort of simplifying a little here.
Okay.
What Herbgrind will actually give you is 4 pieces of information, not just 1. It'll give you the range of all the variables across all executions. It'll give you a range over all the ones that Herbgrind thought didn't go well, had a high local error. It'll also give you an example input in general and an example problematic input. And we give you all of those basically because all of them might be useful, right? The full range tells you basically what inputs must you consider. The problematic range tells you which ones should you, focus on improving. Similarly, the problematic particular inputs. OK, so that's Herbgrind's output. And this is not just slideware. We have an implementation of Herbgrind. It's built on top of the Valgrind framework. That, in fact, is the Valgrind logo. I think it is excellent. So our implementation is 11,000 lines of C. You can go ahead and download it and run it. Herbgrind.ucsd.edu. UCSD is where one of my collaborators is. And we've built it, and we've run it on a bunch of fairly large pieces of numerical software. So things like molecular dynamics simulations or finite element method things. I could go through some charts of figures, but I thought it would be maybe a little more impactful to walk through a recorded demo instead. So let's see if I can get this going. No? Oh, it did? OK. OK, so what I've got here is a much simplified, just for the demo, very simplistic. I'm just evaluating the quadratic formula on a few inputs where it'll happen to be problematic. So we've got the program here. We can compile it. This is ordinary C. And I'm compiling here with -O0 to avoid compiler optimizations, not because Herbgrind can't work with that. And if you run it, you see that we've got all these NaN values. That's bad. We've also got these zeros. Those are a little suspicious, too. So we're now going to run Herbgrind exactly on that binary. It runs, and we can open up the output that Herbgrind produced. So here it is. It's a little more text than what I showed you on the slide. But you can see that, and I've turned off some of the information like ranges here. But you can see that we've got the error, the number of times it's been executed, which you can see that's the iteration count there. And we've got the expression that it is able to extract. And of course, per each expression, we also have this additional information that you might want to look at, which is the local error produced. OK, so this information is great, but we are talking about numerical non-experts. So what are they supposed to do now that they know that this is a problem? So what I'm going to do now, show off another tool that I've been working on, and that'll be the second half of my talk. So Herbie is a tool to attempt to take program fragments like this that have high local error and attempt to improve them. So what I'm going to do is I'm going to copy and paste Herbgrind's output here. I was going to chill out for a while thinking. Herbie internally is doing a search for variants of this expression, ways to change it up that might make it more accurate. And as it thinks, it's going to try to come up with a similar program, in other words, that evaluates a similar expression, but does it more accurately. So let's wait for it to come back here. And of course, you can see how, OK, there it is. So we've come up with this more accurate way of evaluating that expression. And so we're going to take it, we're going to compile it to C, using a little compiler we've written from this expression language. So let's grab this guy, put him in instead of the solve quadratic function. You'll see that there's only one variable. And that's, of course, because only b varied in that loop. And that's part of Herbgrind's detection that some of those are constants. So we've plugged in our new function. We can compile the binary, compile to a new binary, run it. And you'll see that we don't have these nans or those zeros any longer. So that's the sort of workflow that we're hoping for. And now that I've shown you why you might want something like Herbie, something to improve the accuracy of these program fragments, now that you've found problematic ones, perhaps using Herbgrind or maybe using your own intuition, I want to tell you how Herbie works.
I had a question about Herbgrind. Basically, the way I understood was for any instruction, you fix the inputs to be high precision, and then you just check if the result of that. So is wrong, locally wrong or not. But can it happen that maybe locally everything is fine? It's just that because the way computations are happening, over time it gets accumulated, and at some other point it becomes bad, right? So maybe there are 10 instructions that cause it, not a single instruction.
So one of the values of local error, and this is something you can read about in the paper, but I can't put everything in the talk. One of the values of local error is that it effectively allows you to replace low precision operations with high precision ones for reasoning purposes. So there is a strong theorem that if you never encounter any local error, you can think of it as a real number computation. Now, you are right that sometimes error can accumulate slowly. And this is a case for this local error paradigm where you encounter only small bits of local error ever. Like, oh, you're only ever off by like a few floating point numbers. It's never that bad. So Herbgrind has a configurable threshold that you could set to effectively tell it ignore error below this point if you're not interested in this accumulation, or don't ignore it if you don't think there are bigger problems. So you want to look at those situations with lower local error. Generally, this accumulation is harder to catch because it is slower. We've found that a lot of the most surprising problems and the ones that are hardest to debug are the ones where it comes all of a sudden. Because with this accumulating process, you can see it happen iteration by iteration. And that's something that even without numerical analysis expertise, you can do. It's identifying this point where suddenly the thing goes wrong. That's a lot tougher.
Sounds like dealing with memory leaks, which are historically hard to deal with, right? It's the notion of a slow error that accumulates. There's no one place. It's the same argument. There's no one place you can attribute the error to. It's the fact that over some number of iterations. I guess at a higher level, one question I have around this is, so the output is different, right? And the assumption here is like when you look at it, you can tell. But I guess it's an interesting question about do people care if it's different, and if they're okay? There's this sort of weird space where it's good enough, right?
Totally.
And it's the same thing that I call a sensor and I get back a result, and I don't really care too much about how far off it is as long as it's good enough. So how do we get in a world where people care? I guess this is one of the questions.
So there's a few answers to this, and you're right that part of it is that people don't care too much about certain error. And we've talked to people who do this sort of stuff. They have sort of fun stories, like I found a more accurate way of computing something, and my boss said, no, I like the old answer. Right?
That's great.
We know that happens, and that's a human problem that we're not going to solve directly with technology. But there are problems that people do care about, and that is precisely when you get nonsensical results. Because usually you have domain knowledge about what a correct-looking result is, and that might mean I know this matrix is invertible, so I don't want to get an exception that it's not. It could mean I know this function is continuous, so I don't want to get a stippling pattern. That can't happen. It could mean this is supposed to fit within the ring, or any of these other constraints that you have on the output that maybe aren't present in the code, but you care about because it's relevant for something later that you're going to do with those values. And of course, because we're tracking these high-precision real values, we can tell you how much error is there. Now, I don't have any novel arm-twisting mechanisms to make people care. But in some cases, they already do.
I mean, that's a really interesting perspective. The notion that somehow there's this other set of reasoning that goes on in terms of constraints. So this is what you expect, right?
Right.
And one of the problems is that we don't capture those. So it's up to a human looking at the output and actually think a little bit. It reminds me of sort of looking at a machine learning model and looking having a result come out of it and it's sort of like, is this a good one?
Right.
And that world is much worse, right? Because but it's exactly the same problem, right? It's just your problem is easier to sort of put in a box, because there are these sort of relationships between the principal thing you're trying to do and the actual thing.
And we found talking to people that if we ask them, how much error is a good amount of error, they'll say not much, I'm not too picky, but.
But see, this is the challenge, right? At some level, people should care.
Sure.
And somehow we need to help them understand they should care. I think this is really fundamental.
That's part of this inspiration for tying program outputs, which have some hopefully real-world meaning, to intermediate steps in the computation that we're trying to do with Herbgrind. Okay, so this is a great discussion of how do you make people care to focus on this particular numerical issue. There is the separate question, of course, that these are non-experts. So once you focus them in on a spot, they might not know what to do. So that's my transition back to talking about Herbie. And before I tell you how Herbie works, I want to give you some sense of what a human would do to improve the accuracy of a floating point expression. So let's take, again, this quadratic formula. And let's plot the error. And by error, I mean a particular measure called log ops of error. Let's plot it versus that variable b, which you've already seen is the one whose value is particularly important. If you plot it, it looks something like this. So just looking at it, you can see that there are some different ranges of values that seem relevant. So I might break it into 4. A, B, C, and D. And these correspond to different ways that you need to evaluate the quadratic formula if you want the result to be accurate. So in region A, the problem that's happening is that you're getting an overflow in this b squared computation. B squared is infinity. But the actual value of the whole expression is some very finite number. In fact, actually, in this case, close to 0. Infinity is really far from 0. This is a lot of error. To avoid this problem, you want to evaluate an expression that looks quite a bit different. But you can derive it, I promise, using some calculus. And in this limiting case, this computes approximately the correct answer. OK, then we got this region B. Things actually look kind of good in this region B. Not that much error. Like a few bits doesn't hurt people too much. So here, maybe people are OK using the original quadratic formula. This region C does not look quite as good. And that's because here we start getting this problem called catastrophic cancellation. Effectively, what happens is that we are subtracting two very large values to get a very small value. And that means that small value will be heavily affected by rounding error. So in this case, we could do a little bit of a trick and do some algebraic rewriting. Turns out this is algebraically equivalent to that. But they're accurate on different ranges of inputs. And in this region C, this version is more accurate. In B, this one is. So we need to detect these ranges and use the correct one in the correct place.
Is it because you're
that number should be pretty big?
It's actually because here, if b is negative, this is adding two positive numbers. So this is accurate. If b is positive, like in this range, you would be adding a negative number to a positive one. So that's like a subtraction. And in this case, we're doing the opposite. We're subtracting a positive from a negative.
And what is the range of b here? Like negative infinity to infinity?
Yeah, negative like 10 to the large number to positive 10 to the negative large number. Okay, so there's this final region D. This one, again, we have some sort of overflow. And here, the rules of calculus dictate that you get a different weird expression. Let's call them that. So this is a lot of work. It's a lot of math to sit down and do it. It's also a lot of expertise to identify regions A, B, C, and D and note these problems to know what you're trying to avoid. But if you do it, or if you have a friendly numerical analyst who can help you do it, you get a much better error profile. This is something that, while it sometimes has error, is largely going to not run into these problems. And it's going to fix, for example, that complex plotter that we were talking about.
Is it a coincidence that this looks roughly symmetric? Like about 0?
I think it probably is a coincidence. Yeah. I mean, in the ideal case, you'd like a straight line at 0, never any error. But if you don't have preferences about the sign of b, you'd like it to be low on both sides, and that one wasn't like that. OK, so this process is valuable, but a lot of work. We would like to automate it. And that's what Herbie does. So Herbie does this using a search process. It's going to start by sampling some input points that it's going to use to guide that search. So to begin with, we will pick floating point values in the domain of our function. We're going to make sure to pick small values, big values, kind of values in between, positive and negative, et cetera. So with these chosen randomly sampled input values, we can both get the high precision correct answer for that expression, again using MPFR, and we can get the value the expression computes. And not only this expression, but any other candidate expression we come up with. And that lets us measure the error. So this will be a search guided by minimizing this error. That's like our utility or our loss function. And we're going to do this search in a loop where we pick a candidate program, starting from the original, and just attempt to change it, hoping that the error goes down. And the first step of changing it is to find parts of that expression that are most important, most amenable to change. And we're going to do that again using the same local error heuristic that we used in Herbgrind. We can walk up the tree, computing local errors at our sampled input points, and that's going to help us identify individual places in the code, like the cancellation at the addition or the overflow at the square root, that are introducing a lot of local error. If you're interested in why it's the square root, not the squaring, that introduces overflow, I can tell you later. So this gives us parts of the code that need help. And now we need to help them. And our first way of doing that is just algebraic rewrites. So this is pretty standard in computer science. We're going to take this expression focused on that subtree, and we're going to apply a large database of rewrites. And I want to stress that there's nothing numerical in this database. These are more like our axioms of arithmetic. You can see they include fun things like the identity property of 0 and the associativity of arithmetic. So these are all things that you can find in the back of the rhetorical high school algebra textbook.
All these rewrites are equivalence preserving?
Yes. I think all of them are. We actually have a test in the code to make sure that's true. This isn't strictly speaking necessary, because the ones that break your expression will have more error. Right. And so we won't like them. But those also aren't that useful.
Can it happen that it actually is different, but it maybe introduces lesser error?
Yeah, that can happen. We have played with things like that in the past, and we haven't found any examples that are worth keeping in our database. So I might say it's a coincidence that all these are equivalences. OK, so wherever it is that we got these expressions, which are all fairly simple, we can apply them exactly as you expect. So if we want to apply that one, we match the variables, and then it produce the output expression. And here we've done one rewrite, but we can actually do it with backward chaining as well. So that rewrites the expressions. But as you might have noticed on the last slide, the expressions you get are pretty ugly. So we're going to want to simplify them. And simplification is mathematically pretty tough, because you might need to go through a lot of steps. We've actually known since the 70s that it's computationally very hard. We actually have complexity classes for this sort of thing. So we've also got additional constraints on top of just the general problem simplification that we don't want to undo changes we just made. So to try to handle this problem, we use a technique from the formal methods of the SAT-solving community that's equivalence graphs, which let us express, roughly speaking, an exponentially large space of similar expressions in a polynomial amount of memory. And we've got some tricks in here to make sure you don't undo operations, to speed this up, etc. Some domain-specific hacks. So we have a simplifier. And between rewriting and simplifying, you already have something like a numerical analysis search process. But there's another trick that Herbie can pull. And that's what will give us some of those weirder expressions that you saw when I was walking through the quadratic formula. And I like to call these analytic rewrites, as opposed to algebraic ones. Effectively, if you take this expression and look at the cases not only where b is greater than 0, but some limiting case, like b being very large, going toward infinity. Then, after rewriting the formula a bit algebraically, you can apply what you might call an analytic rewrite. And this analytic rewrite is, of course, only true at the limit. But it's useful even before that for numerical reasons. So after you apply that, you can do some more simplification using the same procedure. And that gives you one of these weird expressions. And this is a bunch of fairly tricky code. I can give you details later, but roughly speaking, it works like the Taylor expansions or Taylor series that you might have studied in like a high school or a college calculus class. So these are some ways of mutating the candidate program you started with. And we're just going to go in a loop. At each step of the loop, we're going to keep the ones that improve the error on at least one point. And when the loop is over at a user-specified timeout, or if we don't have any more expressions to look at, we now need to combine all the candidate programs you saw into one actual program that you will execute. We call this process regime inference. Think of it like this. We're going to start with our candidate programs. Let's imagine it's these four. And here I've drawn the error plots versus the variable b. And if you're concerned how I came up with that, we'll actually just try each variable. And whichever works best, we like that one. So what we're going to do with these error plots is overlay them. And from these overlaid plots, you can now imagine walking along the b axis, picking out the variant with the lowest error at every point. And here you can see a little artifact of our sampling. If we don't sample in this region, we might actually get that split point not quite right. So as we walk along, picking out the best candidate to use at every point, we also identify these ranges on which we want to branch among those possibilities.
So this is with respect to a particular choice of floating point representation, right?
Yeah.
So one strategy would just be increasing precision for that part of the computation. Wouldn't that be easier in some ways, or?
I think that's a great question. And the question of precision increases versus rewriting expressions is something we're interested in. There's several other groups working on this as well. One of the fascinating things about that is that the way you lose precision, especially when this problem comes up, not that you iterate a bunch of times and lose a little bit each time, but all the precision is lost at once. The problem you often run into is that adding more precision won't help that much. The behavior might well be, for example, that at every instruction of interest, you lose half your bits of precision. There's a number of bits that will make that work, but that's not a great place to start. So I think there are different cases where you want to apply precision changes versus algebraic rewrites. In Herbie, we're focusing just on the algebraic ones. OK, so regime inference is our last way of combining programs. And by applying it, driving these conditions, that's how we get these accurate results. So Herbie also is not a piece of slideware. We've actually been maintaining it for a while. You can go to herbie.uwplse.org. It's about 10,000 lines of racket code. We've run it on a bunch of things, from open source projects written in a bunch of programming languages to specially chosen numerical analysis textbooks that we gave it as sort of challenge problems. But in particular, if you're interested in using Herbie, we have an online web demo. It's herbie.uwplse.org. That's the same website, /demo. And you can check out Herbie, run it on some expressions. You can also see what expressions other people use. These are fascinating for us, both to see what people are using it for, try to find sources of improvement. Also, sometimes people identify bugs that we need to fix. So do check it out. So I've told you about 2 projects that I've done, and these have been fairly concrete things with goals of helping numerical non-experts write numerical programs. But I want to zoom a little bit back out. Because really, so far, I've told you about these 2 papers. But I started out by citing all these papers. So I have a bit of a broader vision for how numerical non-experts ought to write numerical programs. And that's by using a constellation of tools. You're going to need different tools to help you identify problematic parts of the code and to fix them, or to verify that your fixes are correct, to optimize those results, taking into account numerical accuracy, and any of a number of other tools that I've characterized only very roughly here on this slide. So I've actually been doing a very different sort of project from the 2 I presented a moment ago, called FPBench, over the last year. And this is like a gathering people together and helping them work together project, more so than novel research. So it's been quite interesting for me. In FPBench, we're trying to do some things like create a common format so that different floating point tools can work together. And we even saw this in that brief demo where Herbgrind and Herbie used the same language, and we also used a common tool to compile to C. We've got some formalizations of error metrics. This is one thing that differs between tools, often for important reasons, like different technical ways in which those tools work. Formalizing them, describing how edge cases are handled, makes it easier for those tools to work together. And we've also created a benchmark suite of expressions and short programs gathered from a diverse array of sources. And that's been helpful to get new projects off the ground, check that ideas are working, and so on. So you can check that out, too, at fpbench.org. And actually, on a personal note, this is a very different sort of project to work on, right, than research. There's not a lot of code involved. There are a lot of emails. So it's been rewarding in very different ways.
What does the benchmark mean? Like incorrect and correct thing?
So here, these are individual floating point programs. Often they have some sort of specification. So for example, an error requirement on the output, or they're known inaccurate. So there's something that's useful to focus on. And we are hoping for this benchmark suite to be, it is used for not only improvement projects, but optimization, verification, et cetera. So you can see that we've gathered them from several different projects already. We're trying to pull in more all the time. It's been quite rewarding. And there are some exciting things that have come out of just this ability to put existing tools together. So most recently, for example, we've been working on combining this DAISY tool developed by the MPI SWS folks and our tool Herbie. DAISY is a verification tool, and it can also do some amount of rewriting, much more limited than Herbie, but DAISY is fully sound. So combining these tools has actually given us a lot of cool things basically for free, modulo all the work to make FPBench a thing. So it's given us things like a faster version of DAISY, because it turns out that Herbie's results are easier to verify. This is something we actually would have expected, especially since often DAISY isn't able to understand the expression to the same way Herbie does, because of course it has to be sound. And that limits its analysis. Nonetheless, it's faster at verifying Herbie's output. At the same time, we get a validated version of Herbie. You can run Herbie and then check that it's more accurate. And this also gives us the ability to compare different research projects. So for example, we've been able to compare the rewriting algorithms in Daisy and in Herbie. And that's helped identify places that each can improve. So it's been great to do that sort of collaboration, even though that means waking up early to be on European time, and they have to stay in late at the office. But this sort of coordination has been rewarding and surprisingly fruitful for how little technical work had to be put into it. So that's a bit of the broader vision for how I think Herbgrind and Herbie can fit into a bigger goal of helping non-experts write numerical programs. So thank you. I'd be happy to take any further questions. And if you're interested in any of these tools, please check them out.
So, I mean, for me, this is great work. I'm really excited. I think that revisiting kind of these computations and how they influence the outcomes is really important. But I still have this kind of sense of loss, maybe, about the relationship between how people execute in practice and this kind of better way to understand what's going on. And certainly the rush in the neural network space, right, around building these things. And
building things like half-width precision and so on.
Well, I was going to say, I mean, they're throwing all kinds of stuff at trying to solve these problems, and they're losing the ability to really understand, but they don't care, right? It's sort of like, let's just rush into this and build these things because they can do stuff we just couldn't believe could happen, right? And there's this sort of element of the unbelievable about these neural networks that makes people not even think about this stuff, right? They don't even want to think about it, right?
But I think one thing that we've seen is that the community of people who use floating point is incredibly broad, because it doesn't include just computer scientists. Again, I mean, as I said, right, my numerical analysis class was taught by a physicist, because they do simulations and they need to know. It's engineers, it's scientists. These days, it's social scientists and economists. One thing we had a lot of fun running is the Federal Reserve Bank of New York model of the U.S. economy.
Oh, awesome.
That's a lot of numerical computation. And that is stuff with real-world impact. We didn't find too many problems, so that's good. Numerically. I don't know about the model itself, but numerically. These people often do have great concerns about their numerical accuracy, and often not in the form of, I need my error bounds at 10 to the negative 12th, and I'm only getting 10 to the negative 10th. But they do have, which would be, of course, great. That's the stuff that's easy to work with. That's sort of modular reasoning. But they do have concerns like, sometimes my rocket fails to solve its optimization problem and then just turns off its engine. I'd like that to happen less frequently. And that's something that we've seen with Air Astro people at the University of Washington. Or they have concerns like, my PID controller sometimes puts the thing in the wrong place for a robot. That's a concern that transcends maybe the micro view that, as programming languages people, we'd like to have, and this concern about actually measuring error at every point and so on. But these end-to-end results are things people care about, and some of our tools help transform that into this more common PL notion of looking locally at operations and building up in a verified way.
Yeah, I mean, for me, I think the real question is there a sweet spot here where there's a domain, an emerging domain? It seems like self-driving cars kind of fall into this engineering category where clearly there's a lot of engineering, the classic, controllers and things like that going on, and obviously it's a high reliability environment, right? And so, the issues that come up here, it seems like that would be. I'm just trying to think about where it's like a tipping point argument. It's like, where is the place where people care the most about this and where it'll have the most impact, so that the shifting. I mean, at some level, you talk about non-experts or whatever, but at some level, everyone that builds software these days has to be at some level an expert or understand this.
At something, yeah.
And, and understand that there are variations and stuff happens, and it's not just the floating point. I mean, there's all the different dimensions. This whole project uncertainty that was done here, kind of sort of tries to bring the distribution of values that you get out of these things into the the abstract framework of the programmer. But but at some point, I guess my makes sort of sense is here. This stuff is happening, and you're right. And there are domains in which people have written code like this, but but the broader audience is really needs to be brought into this world, needs to be introduced to it. And one of the questions is, what do you tell them about this stuff? How do you make it clear that they should be concerned? I mean,
yeah. No, I mean, I think these are great questions. Certainly, I'm not the only person thinking about them, which is why we've got a lot of very different attempts at figuring out what is the key tool to build or key tool to attack. I think that's why a combination of approaches is important. And it's not just, as you mentioned, bringing down the cost. It's also, as you mentioned, proselytizing, getting people more concerned about their numerics. But there's some technical work that has to happen too.
So after working on this for quite a while, can you build like a repository of common issues, something of that sort, that you can educate people about and attack them preemptively?
Maybe. I did a talk at the people who make MATLAB on this topic. And this is one thing they were very interested in. They know what numerical issues people have. Let me switch to mirroring. They know what numerical issues people have. They just need tools that can help people use their customized solutions to them. If you look at, this is the web demo. If you look here, you can see what sorts of, just kidding. Yeah. I don't want to step through the flow now. I've been through that flow before, and I don't like it. OK, you could go to this site and click there. And there are at least several hundred, I haven't checked in a few months, several hundred formulas that people have submitted. I don't have answers as to why exactly. But given the people who are on our mailing list who submit bugs, these are people with all sorts of interests. Designing power management systems in France, or a library for engineers to use for finite element modeling. And the web demo is how some of them use Herbie. So you can see what formulas people are submitting. And those are some sense of common issues.
For many applications, like the neural networks in this case, oftentimes you don't really have an obviously wrong result.
Right.
You have the result that seems bad, but you cannot pinpoint, is it because of the algorithmic error, the capacity of the model, etc. Or maybe there is a deeper numerical issue which
That's right.
I certain has happened at some point in the history of humankind.
Yeah, actually,
in the world of neural networks. But
at NIPS, there was this excellent paper on using floating point rounding error as a feature, right? This is a funny paper, but. Yeah, it's especially with neural networks, which are so resilient to error that, if the output's wrong, you have no idea what sorts of errors it was resilient to and which ones were problematic. Yeah, that sort of thing is tough.
Use these kind of errors as additional
regularizer.
Yeah, some kind of regularization on top, and it actually produces better results.
Yep.
So it's funny.
I've heard these stories too. I think machine learning is a particularly challenging domain for wondering about numerics issues. And certainly there's some special purpose work people are doing on, for example, really understanding the numerical properties of, for example, stochastic gradient descent.
One more question I had. This was really cool. I was thinking, going forward, do you think there's actually some kind of value in actually? So most of the rewrites look a little bit local, like we're doing expression by expression. But doing it at more holistic level to the program itself, or doing bigger changes, is there value to do that, or like most of the interesting ones are local anyways?
We did a pretty long-term exploration of rewriting. This isn't going all the way to the program, but rewriting loops.
Yeah.
So, for example, you might have the issue that you sum a bunch of floating point numbers. That's a bad idea, it turns out. Or you got to do it right. Sorry, obviously you got to sum them if you got to sum them. Or looking at, if you have to solve a differential equation. There's actually a lot of ways you can attempt to change that. For example, you can do 2 steps of the loop at a time. And then between those, you might be able to do some numerical stuff to make it more accurate. We looked at that sort of thing. Part of the challenge was getting good benchmarks to guide our approach. One of the things that helped make Herbie a success was the existence of numerical analysis textbooks that focus on this particular topic. So we can have Herbie take the class, give it the problem sets and see how well it does. We found that there are broader patterns that you could apply there. And there are some patterns that are fairly easy, like you can apply a compensated summation. There are also patterns that we know practitioners use. They say, oh, this sort of problem happens because we're using a cubical grid. If we were to use a hexagonal grid, this problem would go away. That's a very high-level way of thinking about what the program is doing, but it is something you can imagine Herbie replicating. And for example, trying out different grid arrangements. I think that would be fantastic work. We've done some of it. One of the inspirations for Herbgrind was to get benchmarks from large numerical programs. I think that's a valuable way to proceed. Another thing that Herbie alone doesn't do, and something that would be interesting to explore, is Herbie is operations on floating point numbers, double precision numbers. What about on matrices? Right, matrices are interesting because there's a lot more parameters in which they can be special. Right, a tridiagonal matrix has very interesting properties that go into a solving routine or a QR factorization routine. So that's something that we think would also be interesting to look at. And I think that gets to a broader issue of how do you look at libraries. Right, here we think of sine and square root as a primitive operation, even though it's a library. Why not look at matrix factorization that way, and so on. At a high level, you can imagine, what about SGD? That's a library. Maybe I can know something about the library and reason about my input to it separately. I think that's really interesting work. I would love to do it. Haven't done it yet, but there's time yet.
Yeah.
All right, great.